Okay. Oh, algebra. This is lecture 4, not lecture 3. This is just the 4th class. And last week we talked about permutations in the symmetric group. Any questions about that or about any of the homework problems? Okay. Then the lesson for today and Wednesday, and if you check the calendar, you'll see that a week from today, next Monday, is a holiday, President's Day, I guess. So we have class today, we have class Wednesday, and the next class will be a week from that, the following Wednesday. And what we're covering today is section 1.6, which is divisibility in the integers. So the integers.
Excuse me, Professor.
Yes.
Can you do question number 5 from the homework?
Okay, so let me pause for a moment and look for question number 5. So this is 1.5.5. Is that the question?
Yes.
Okay. So let me erase this. So this is on permutations. Permutations. Exercise 1.5.5. We want to show that any K-cycle can be written as a product of 2 cycles, and therefore any permutation can be written as a product of 2 cycles. And it's, as a kind of a hint, it says to look at problem 1.5.3, but let's just try and do it directly. So a K-cycle is a permutation of the form A1, A2, A3 up to A sub K, where these are distinct. No 2 of them are the same. Distinct integers. And this permutation, since A1 to A2, A2 to A3, A3 to A4, and so forth. Eventually we get to, let's say, A sub K minus 1, the next to the last term, which gets sent to AK, which is the last term, which gets sent back to the first term. So that's why we call this a cycle. We can think of these numbers as being in a circle, and we just move the permutation, sends one number to the next number in the circle. And a 2 cycle, so K is the number of integers, a 2 cycle just has 2 integers, A1, A2. So A1 goes to A2, and A2 goes back to A1. And the first part of the problem is to show you can write any K cycle as a product of 2 cycles. So of course, we can start with 3 because any 2 cycle is a 2 cycle. So suppose we have a 3 cycle, A1, A2, A3. So the picture of this would be A1 goes to A2, A2 goes to A3, and A3 goes back to A1. And what we want to do is somehow decompose this into a product of 2 cycles. And let me just make a lucky guess about how to do this, because really it's part of it is just trial and error. So suppose I write down the A1, A2, that's a 2 cycle, times A2, A3. So this is a product of 2 cycles. So what is this permutation? This permutation, so let's follow A1, A2, and A3. This sends A1 to A1, and then this sends A1 to A2, so A1 ends up at A2. This sends A2 to A3, and this sends A3 to itself, so A2 goes to A3. This sends A3 to A2, and then this sends A2 to A1, so A3 ends up at A1. So in this so the product of these two cycles is this permutation. And what is this? That's A1 to A2, A2 to A3, A3 back to A1. So this is exactly the 3 cycle, A1, A2, A3. So what we have is, let's say, the first step in the proof, I showed that every 3 cycle is a product of two cycles. All right? So this is the first step, and the first step is always important. So you need to take a look at this before I go on and ask me if there are any questions. Okay? So every 3 cycle is a product of 2 cycles. Suppose we had a 4 cycle. So let's apply the same trick or the same method. Here, I took the 3 cycle and I separated out the last 2 and the first 2. So just as an experiment, let's take the first 3, A1, A2, A3, and then times the 2 cycle, A3, A4. All right? And let's see, what is this permutation? Right? So this is not a product of 2 cycles. This is a 4 cycle, is a product of a 3 cycle and a 2 cycle. But I know that every 3 cycle is a product of 2 cycles. So if I can prove this, then I'm almost done in the case of 4 cycles. So let's look at this. A1 goes to A1, goes to A2. A2 goes to A2, goes to A3. A3 goes to A4, goes to A4. A4 goes to A3, and A3 goes back to A1. So this 4 cycle is a 3 cycle times a 2 cycle. But we know that A1, A2, A3 is A1, A2, A2, A3. So if I take this and I substitute this in here, I get that the 4 cycle is equal to A1, A2, A2, A3, A3, A4. So this proves that every 4 cycle is a product of 3 2 cycles. Okay. And now we can do what is called a proof by induction. So it's absolutely essential that you learn in this course what is mathematical induction and how to use it in a proof, because we will use induction over and over and over again. So suppose, let's say, P of K is a statement or a proposition about the integer K, some positive integer. So induction says that if P of 1 is true, so whatever the statement is when K equals 1, we know that's true. And if whenever P of K is true, then P of K plus 1 is true. Actually, maybe I should start it off. Well, all right. Then P of K is true for all K. So this is a fundamental principle, axiom, if you like, in mathematics. If there's some statement about integers K, like whatever it might be, every K cycle is a product of two cycles. If you can prove it for some number 1, and if you can prove whenever it's true for K, it's true for K plus 1, and then it's always true. And you don't have to start with K equal 1. You can start with any integer that's called K naught. So if f of K naught is true, and if whenever P of K is true, P of K plus 1 is true, then this proposition P of K is true for all K greater than or equal to K naught. Because let's say K naught is 1. You know it's true for 1. And this says if it's true for 1, it's true for 2. But then this says if it's true for 2, it's true for 3. And this says if it's true for 3, it's true for 4. And that goes on and on and on forever. So that is the principle of mathematical induction, which we use to prove things all the time, over and over and over again. This is, you absolutely, I mean, really, you can't pass this course without being able to give a proof by induction, because many, many proofs will require this. Okay. So in our case, what is our proposition P of K? It says that K be equal to or greater than 2. P of K is the statement, the proposition, that every K cycle is a product of two cycles. So P of 2 is true, namely A1, A2 is a 2 cycle. So it's a product of 1, 2 cycle. And I proved that P of 3 is true. In fact, I showed that A1, A2, A3 is equal to A1, A2 times A2, A3. So this 3 cycle is a product of 2 cycles. And I proved that P of 4 is true. I showed that A1, A2, A3, A4 is a product of 3 2 cycles. A1, A2, A2, A3, A3, A4. So this proposition is true for K equal 2, 3, and 4. So let's give a proof by mathematical induction. So assume P of K is true. We must prove P of K plus 1. So I claim, how do I prove this? I claim if I take a K plus 1 cycle, that I can write this as this K cycle times the 2 cycle AK plus 1. So the first step is to prove this algebraic identity. The product of a K plus 1 cycle is a K cycle times a 2 cycle. And again, how do we prove this? We just apply this. We compute this permutation. What is this? So we just follow all the numbers around. If you take A1 goes to A1 goes to A2. A2 goes to A2 goes to A3. When you get up to, let's say, A sub K minus 1, A sub K minus 1 goes to AK minus 1, and this sends AK minus 1 to AK. Then what about AK? This sends AK to AK plus 1, and this sends AK plus 1 to itself. And this sends AK plus 1 to AK, and this sends AK back to A1. So in fact, this K cycle times this 2 cycle
Can you move up a little bit?
is equal to this k plus 1 cycle. But by the induction hypothesis, we know then that A1, A2, AK plus 1. So I just showed this is A1 up to AK, a K cycle, times AK plus 1. And this, by the induction hypothesis, is a product of two cycles. In fact, we could have made the induction hypothesis that this is A1, A2, A2, A3, A3, A4, all the way up to A sub K minus 1, A sub K, that's this, times this. And what we have over here, this is K, two cycles. So that's the proof that so this is a proof by mathematical induction that every K cycle is a product of two cycles. Right. So this is the first part of exercise 1.5.5. All right. And what's the second part of the problem? To show not only that every K cycle is a product of two cycles, but every permutation is a product of two cycles. But for this, we use the following fact that sigma be a permutation. So we know that every permutation is a product of disjoint cycles. That was the theorem. So we can write sigma as some cycle, A1 up to A sub K, times another cycle, let's say AK plus 1 up to A sub L, and so forth. You have a whole series of cycles, say AM plus 1 up to AN. So you can write every permutation sigma as a product of pairwise disjoint cycles. So these are cycles, and each of these is a product of two cycles. So you take your permutation sigma, you write it as a product of disjoint cycles, and we just proved that every cycle is a product of two cycles. So here we have two cycles, here we have two cycles, here we have two cycles, and so on. So that's the end of the proof. Now, I will say that if this is the first course in, let's say, real mathematics that you've taken, by real mathematics, I mean, it's certainly beyond calculus, where you are dealing with abstract concepts and proving theorems about them, then it takes a lot of time and sort of thinking in a quiet place to understand these kinds of arguments, but this is what you do in mathematics. This is what you have to learn. Okay. Other questions about this? Again, this is all being recorded, all posted on YouTube. And so it's worth looking at a couple of times, perhaps, if you to help understand.
Professor, the last one you explained is from the homework, or it just
This is problem 1.5.5.
okay. No, the one let sigma, you already proved that in induction. I
This-
don't get this
I
part.
didn't
Yeah.
prove this before. Before I proved that every K cycle is a product of two cycles. This is to
Okay.
prove that every permutation is a product of two cycles, because not every permutation is a K cycle. Right?
Confused on it.
I mean, if you take the permutation sigma equal 1, 2, 3, 4, 5, 6, this is a permutation. It's not a cycle. It's a product of 2, 3 cycles. And then you can write this as a product of two cycles. But this is not a cycle. But we use the fact that every permutation decomposes into disjoint cycles, and then we use the fact that every cycle is a product of two cycles.
Okay.
Any other questions about this?
Thank you, Professor.
Okay. All right, so let's go on now to section 1.6, which is divisibility in the integers. So the word for number or numbers in German is Zahlen, which is historically why we use the letter Z to denote the set of all integers. 0, plus minus 1, plus minus 2, plus minus 3, and so forth. So wherever you see in the text, it will always appear as, sometimes it will appear as a boldface letter Z. Z stands for Zahlen. That's sort of irrelevant to us, but this is the set of all integers, positive, negative, and 0. And what are sometimes called the natural numbers are the positive integers. And that's often denoted by this sort of boldface letter N. So this is the set of just the positive integers, 1, 2, 3, 4, 5, and so forth. 0 is not positive. And 0 is not negative. 0 is 0. Right? So the integers divide into three sets: the positive integers, the negative integers, and 0. N, I mean, sometimes it's a little confusing. N does not stand for negative. It stands for exactly the opposite. It stands for natural numbers, which are the strictly positive integers, not 0. Right. So that's our standard notation. And N is non-negative, an integer, if N is in the set of positive integers union the set 0. So this means the union, what you get by combining two sets. This is the set whose only element is 0. This is the set whose elements are the positive integers. So the union of these are the integers that are positive or 0, which means not negative or non-negative. So that's what non-negative means. And recall the absolute value. The absolute value of a number, a real number, is A if A is greater than or equal to 0, and it's minus A if A is negative. So the absolute value of a number is always non-negative. And in fact, the absolute value of a number is 0 if and only if the number is 0. If A is positive, the absolute value is positive. If A is negative, the absolute value is positive. The only times A has absolute value 0 is when you have the number 0. Okay. And you learned in elementary school how to add and multiply integers, right? That's arithmetic. So what are sort of the properties of addition and multiplication of integers, or addition and multiplication in the set Z of integers? So the first property is, for all integers a and b, a plus b equals b plus a. That means, in mathematical language, addition is commutative. And also, a times b is b times a. So multiplication is also commutative. All right. For any three integers, if you add a plus b plus c, that's the same as a plus b plus c. Addition is a binary operation. You do it to two things at a time. So if you have three numbers that you want to add, you can add first a plus b and then c, or you can add b plus c and then add a to that. And well, this property is called associative. Addition is associative. And the same is true for multiplication. A times b times c is a times bc. So multiplication is also associative. Okay. Then there's an identity element. 0 in the integers has the property that 0 plus a plus 0 is a for all a in the set of integers. In other words, 0 is an identity element for addition. And for multiplication, the number 1 has the same property. 1 satisfies 1 times a, and a times 1 is a for all a and z. So 1 is the identity for multiplication. Right? For addition, but not for multiplication, there's an additive inverse. So for all a in z, every integer a, there is a number minus a in z, such that a plus minus a is 0. So this is called the additive inverse. Right? And note, this is not true for multiplication. If you take the number 2, for example, 2 times any number b is never equal to 1. So there does not exist an integer b such that 2 times b equals 1. Right? 2 times b is never 1 for an integer. So in the integers, multiplication has many nice properties, but there's no inverse for an element. Right? That's why we had to invent fractions. But a fraction is not an integer generally. What are some more properties of addition and multiplication? Again, you learned all of this in elementary school without using fancy words, but you certainly know the properties. So we have a distributive law. If you have A times B plus C, that's AB plus AC for all integers A, B, and C. Okay. And then two other final remarks. One is N, which is the positive integers, is closed under addition and multiplication. That is, we know the integers are closed under addition and multiplication, but so are the positive integers. The sum of two positive numbers is positive. The product of two positive numbers is positive. And there's one other property that's very important and always often considered so obvious that you don't think about it, but it really is very important. The product, if you multiply two non-zero integers, positive or negative, doesn't make any difference, is always non-zero. Another way of saying that is, for all integers A and B, if A times B is different from 0, then A is different from 0, and B is different from 0. Actually, it's not quite the same, but it's also true. So really, a more correct statement of these two facts is that the product of two integers is non-zero if and only if both of them are non-zero. So that really is the statement. And again, let me add just one or two other things which are kind of obvious, but it's worth writing down. For integers A and B, A is greater than B if and only if A minus B is positive, and A is greater than or equal to B if and only if A minus B is non-negative. And this double-headed arrow means if and only if. So there's lots of mathematics notation that you have to learn, and this is one of these things. Okay. Any questions about this so far? So we notice that there's a certain symmetry between properties of addition and properties of multiplication, except for the fact that in the integers, there's not necessarily a multiplicative inverse. That is, there are no two integers that, if you have, there's no number b such that b is the inverse of 2 in the integers. 2 times b is 1. It's not possible. And this leads us to what is a very fundamental concept in algebra, which is called divisibility. And again, you learned this in elementary school or junior high school or wherever it was that you learned long division, right? You know, you can't always divide one integer into another evenly, but you can always divide it with the remainder. So I want to prove these general properties of divisibility. And the first thing is the definition. So this really deserves a star, because we're going to use this a lot. So we're only working in the integers. In section 1.6, this is only about the integers. So we say that A divides B. This is what we're defining. If there exists an integer q, which is called the quotient, such that a times q equals b. So for example, and the notation is, if a divides b, we write a and then a vertical line and b. So this is really very important notation. So for example, 3 divides 21 because 3 times 7 is 21. And the 7 is the quotient. So here, a is 3, b is 21. 3 divides 21 because 3 times some number q, this case q is 7, is equal to 21. Or 13 divides 1001 because 1001 is 13. I think this is right. You have to check this. 13 times 77. Okay. 13 times 77 is 1001, so 13 divides 1001. Okay. Any questions about this? All right. So what is proposition 1.6.2 in the text is properties of divisibility. Suppose we let A, B, C, U, and V be integers. So the first property says that if U times V is 1, then either U and V are both 1, or U and V are both minus 1. I mean, the converse is certainly true. If U and V equal 1, the product is 1. And if U and V are both minus 1, the product is plus 1. So the proposition says the converse is true. If the product of two integers is 1, that can only happen in one of these two cases. Okay. The second part says if A divides B and B divides A, that is, you have two integers and each divides the other, that can only happen is if A is either equal to B or minus B. So A is plus or minus B. And again, let's just note, if A equals B, then A times 1 equals B, so A divides B. And if A equals minus B, then A times minus 1 is minus B is B. So again, A divides B. So the converse is trivial, but the harder part is to show that if A divides B and B divides A, that happens only when A is plus or minus B. The third is a statement that divisibility is transitive. And what transitive means is the following. If A divides B and B divides C, then A divides C. And the fourth property says that if A divides B and A also divides C, then A divides every integer that's a linear combination of B and C with integer coefficients. A divides every number of the form SB plus TC for all integers S and T, all S and T in the set of integers. Right? So I suspect that you would be happy to accept all of these statements, but we need to prove them. But certainly they're all plausible. So algebra is a subject where things have to be proven. So let's prove A. So suppose U times V equal 1. So if the product of two integers is not 0, then U is different from 0 and V is different from 0. Otherwise, the product would be 0. So suppose, first of all, that U and V are positive. So let's say U is greater than or equal to V. They're all greater than or equal to 1 because they're positive. And if they're positive, in any case, if you have any two numbers, one is always greater than or equal to the other. So if U greater than or equal to V greater than or equal to 1, that means U times V is at least, V is at least 1, U times 1, or U, which is equal to greater than or equal to 1. But U times V is equal to 1. So the only way this inequality can be true is if V equals 1, right? Because if V were 2 or greater, 2 times U is bigger than U. So U equals V equals 1.
Professor, can you move up a little bit?
Right? So suppose we don't assume they're positive, but if UV is 1, then the absolute value of UV is the absolute value of 1. And the absolute value of 1 is 1, and the absolute value of UV is the absolute value of U times the absolute value of V. So the only way this can happen, well, these are now positive, because the absolute value of a non-zero integer is positive. So this says the absolute value of U and the absolute value of V are 1. And the only numbers that have absolute value 1 are plus or minus 1. And if you take plus or minus 1 times plus or minus 1, the only times UV equal 1 is either they're both positive or they're both negative. Because if one were positive and the other were negative, the product would be negative. So the statement A is kind of obvious, perhaps, but it needs a proof, and this is a rigorous proof. So if the product of two integers is 1, the integers are either both are either both plus 1 or both minus 1. Okay. Are there any questions about that? All right. What's the second statement we have to prove? If A divides B and B divides A, then A is plus or minus B. So let's see. If A divides B, that means B is A times some number. B is U times A. And if B divides A, then A is some multiple of B. And if you put these two together, what does this say? This says that A equals V times B, but B is U times A. So A is VU times A. Now, If a is different from 0, you can divide, right? If a is VU times a, that means VU equals 1, which means V equals U equals plus or minus 1, which means B, which is U times A, is plus or minus A. And that's the whole proof. If A is 0, then B is 0. And 0 is plus or minus 0. So the only interesting case is when A is non-zero. The third thing we need to prove is transitivity. If we have integers a, b, and c, if a divides b and b divides c, then a divides c. So how can we prove that? If a divides b, then b is u times a. If b divides c, then c is v times b. If you put this together, c is v times b, but b is u times a. By associativity, this is vu times a, so c is some integer times a, so a divides c. And that is the complete proof of transitivity. And what is the last item we have to prove? If a divides b and a divides c, then a divides sb plus tc for any integers s and t. So let's prove that. A divides b means b is u times a. A divides c means c is v times a. So suppose I take a number of the form SB plus TC. I want to show this is divisible by A. So SB,
Professor,
B is
yes, one question. So the U and V is the quotient?
here? Yes.
Yeah.
Yeah.
Okay.
Right. A divides B means B is some multiple of A. It's U times A, and that multiple is the quotient.
Okay.
So SB is S times UA, and TC is T times VA, which I can write as SU times A plus TV times A by associativity. And I can write this as SU plus TV times A by distributivity. This is the distributive law. And if I call this number Q, this is Q times A. So A divides SB plus TC no matter what numbers S and T you choose. And that is the proof. Okay. Now, it's nice to try to reduce things to their simplest form, like water, if you reduce it to its simplest form, is hydrogen and oxygen, right? Those are the atoms that make up the water molecule. Suppose you take an integer like 42, I can write that as 2 times 21. I can factor it. And I can factor 21, that's 2 times 3 times 7. So 42 is the product of each of these three numbers, and none of these can be factored any further. These are like the atoms that make up the number 42. Or we saw before that 1001 was 13 times 77. 13 I can't factor, but 77 is 7 times 11. So 1001 is 7 times 11 times 13. And these are all 7, 11, 13, 2, 3. These are numbers that don't factor, and they're called prime numbers. So a prime number is an integer, let's say p, strictly greater than 1, that is not divisible by any natural number except itself in 1. So 2, 3, also 5, 7, 11, 13, 17, 19, 23, 29, 31, 33, 37. These are all prime numbers. They're
25?
all, what?
25?
Sorry, which number?
20.
25 is 5 times 5.
Yeah, that's sorry. Okay.
So these are all examples of prime numbers. And I think these are all the prime numbers up to at least 53. The next one would be 59 and so forth. But there are a lot of them. These are all prime numbers. Number 1 is not a prime. Right? And prime number is strictly greater than 1. And it has no divisors except 1 and itself. So that's what it means for a number to be prime. And a very important result in the history of mathematics, we'll prove 2 in a moment. The first says that every natural number, n, strictly bigger than 1, is a product of prime numbers. Product means, it doesn't mean 2 or 3, it means any number at least 1. So for example, 2 is 2, that's a prime. 3 is 3, that's a prime. 4 is 2 times 2, product of primes. 5 is 5. 6 is 2 times 3. 7 is 7. 8 is 2 times 2 times 2. 9 is 3 times 3. These are all products of prime numbers. 10 is 2 times 5. 11 is 11, it's prime. 12 is 4 times 3, but 4 is not a prime, but 4 is 2 times 2 times 3. So 12 is a product of 3 prime numbers, 2 taken twice plus 3. 13 is a prime. 14 is 2 times 7. 15 is 3 times 5. 16 is 2 times 2 times 2 times 2. It's a product of 4 primes, and all 4 primes are equal to 2. 17 is a prime. 18 is 3 times 6, but 6 is 2 times 3. So 18 is 2 times 3 times 3. 19 is 19. 20 is 4 times 5, and 4 is 2 times 2. So 20 is 2 times 2 times 5. 21 is 3 times 7. And so on. It's a lot of fun trying to factor integers. In fact, it's easy to factor small integers. I mean, integers up into like the hundreds of millions are actually easy to factor. By easy, what I mean is, for example, if you took calculus lab and you use Maple, there's a simple command in Maple to factor an integer. And if you plug in a number like in the hundreds of millions, Maple will factor it. But it's a very important fact that for really big numbers, and by really big numbers, I mean numbers with thousands and thousands of digits, there's no computer built in the world ever that can factor a large integer. And almost all international banking and international commerce is based on the fact that you cannot factor large integers. So if you buy something on Amazon, you put in your credit card, and your credit card is transmitted, so Amazon can get paid. But there's a principle in computer science that every computer message can be intercepted and read by an antagonistic party, the enemy, whoever your enemy happens to be, just someone who wants to steal your money or whatever. And so before Amazon transmits your credit card number, it encodes it, it encrypts it. It uses some way to disguise the number. And the basic way used for encryption depends on the fact that it's not possible, as far as anyone knows, at this point in history, to factor a very large number. So your credit card, which is 16 digits, maybe plus an expiration date and a secret code. So you're up to, 22 or 23 digits. That's a pretty small number, but it's translated into some humongous number. And only if you know the method of putting into that big number can it be factored in a way to recover the number you started with. And so anyone can steal the encrypted credit card, but because they can't factor very big numbers, they can't figure out what your credit card really is and steal your money. That's the basis of all international commerce. Whenever Chase Manhattan Bank sends $100 million to, another bank somewhere, it's all done electronically. And if you could break the code, you could steal the $100 million and be very happy somewhere. But no one knows how to factor these numbers. But small numbers, you can do it, and it's fun to do. So here I factor the numbers from 2 to 21. Right? And the proposition says this is always possible. Every natural number greater than 1 is a product of prime numbers. Okay? So how do we prove that? Well, we're going to prove it by mathematical induction, which is the way we prove almost everything in algebra. So this is a proof. So let's say P of K is the statement that K is a product of primes. So P of 2 is true, right? Because 2 is equal to 2. In fact, I just showed that P of K is true for all K from 3 up to 21, right? Because here I actually wrote down a list of these first 20 integers bigger than 1, and I wrote them as products of primes. So we know this is not only true for 2, it's true for 3, 4, 5, everything up to 21. So I want to prove by induction that if something is true for K, so I want to show that P of K true implies P of K plus 1 is true. So how can I do that? So there are two cases. Case 1, K plus 1 is prime. In case 2, K plus 1 is not prime, right? Those are the only two possibilities. If you have an integer bigger than 1, it's either prime or it's not prime. But if K plus 1 is prime, then we're done. Because k plus 1 is k plus 1. That's a prime. So we're done. So the interesting case is when k plus 1 is not prime. Not prime means it factors. That means k plus 1 can be factored into a times b, where a is at least 2 and b is at least 2. And if the product a times b is k plus 1, in fact, a is at least 2, but it's less than k plus 1, and b is at least 2, and it's also less than k plus 1, or less than or equal to k, right? Because if one of these was k plus 1, the other would have to be 1, but neither of these is 1. So this is a product of two numbers, and they're between 2 and k. But we're assuming p of k is true. That means, what I mean by that is every integer k or smaller factors. So p of a is true. So a is some product, p1 up to p sub r, product of prime numbers. And p of b is true. So b is some product, p1 prime up to p sub s prime. So k plus 1, which is a times b, is the product of these r primes times these s primes. And we're done, because k plus 1 is now a product of prime numbers. So that's a proof. And when you understand induction, it's very simple. And when you don't understand induction, it's very hard. And the way you get from it being hard to being simple is to spend a lot of time really thinking about everything that's written here. And it's all written out in detail in the text, and the text is legible. So every integer greater than 1 is a product of primes. And it's a natural question to ask, how many primes are there? So this is one of the most important problems in the history of mathematics and science. And it was actually solved by Euclid. Sometimes people think Euclid only wrote about geometry, but in his books, there was much more than just geometry. And in Book 9, Proposition 20, Euclid proved there are infinitely many primes. There are infinitely many prime numbers. Okay, so this is really important, and it's 100% certain that on the midterm or the final or both, you will be asked to prove this theorem, that there are infinitely many primes. Well, how can we prove this? So it suffices to prove that given any finite set of primes, say P1, P2 up to P sub k, there exists another prime called P sub k plus 1. That is, if there are only finitely many primes, and I wrote them all down, you couldn't find another prime. But if given any set of primes, say k primes, I can always find another one. That proves that the set of primes has to be infinite. So even this takes some thinking to get used to, but so here's what Euclid said. Let capital M, here I have a finite set of numbers. You can always multiply a finite set of numbers, not an infinite set, but You can always multiply a finite set. Suppose I multiply these k primes together. So that's some positive integer, and I take that and I add 1 to it. So this is the very, very clever idea. Take the product of all these primes and add 1. Now, this number m is not divisible by the prime p1, for example, because, let me just write this down explicitly. Suppose p1 divides m. That means that m is some quotient times p1. But m is equal to p1 times p2 up to p sub k plus 1. So if I rearrange this, this says that, let me write this as p1q. p1q minus p1 times p2 up to p sub k equals 1. And if I factor out the p1, this says p1 times q minus p2 up to p sub k equals 1. So here I have a product of two numbers equals 1, and that can only happen if these numbers are plus or minus 1, but p1 is a prime, 1 is not a prime. So this is impossible. So m is not divisible by p1. And the same argument works for p2, p3, any of these numbers. So m is not divisible by any of the numbers p1 up to pk. But this is a number bigger than 1. It's 1 plus something. And I proved a moment ago that every number bigger than 1 is a product of primes. So some prime, called p sub k plus 1, divides m, and p sub k plus 1 is not any of these first k primes that we started with, because none of these primes divides m. So given any k primes, I just proved, or Euclid proved, really, that there's a k plus first prime different from any of them. Okay. This is Euclid's proof that there are infinitely many primes. This is in the text, proposition 1 or theorem 1.6.6. And this you absolutely positively have to understand completely. This kind of argument we use over and over again, and again, unless I forget, but it's certainly my intention that one problem on the midterm will be prove Euclid's theorem that there exist infinitely many prime numbers. Okay. All right, so this is the beginning of section 1.6 on divisibility, and we're going to continue to discuss this on Wednesday and then again next Wednesday. But this is really a very, very important section, and the more time you spend studying section 1.6, the much better off you will be. Any questions about any of this? This is all I want to do today. There's a lot to go through and for you to go through and think about. And they remind you we have office hours this week, the same as last week. So there's one this evening at 7 o'clock, I believe, and Wednesday at 1 o'clock and Friday at 11 o'clock. So, and if you have questions and can't make one of those times, send me an email and we can just arrange another time when we're both available. Okay.
Professor, I already submitted the homework, but I didn't prove with the induction, so I just learned from you. So can I resubmit it again?
Oh, yeah, the homework on Blackboard is set up so you can resubmit as many times as you like. It's
Okay.
automatic.
Okay.
There's no problem doing it. Any other questions? Okay, then we're done for the morning. Everyone be well. It's not too cold out today, so good. See you on Wednesday. Bye all.